Now, I mentioned that there are stars that are so far away from us that we cannot resolve them as two separate stars by the telescope, like we could for that Kruger 60 binary system. And that second group are so-called spectroscopic binaries. And to detect them, we rely on what is known as the Doppler effect. So let me discuss briefly the Doppler effect, and all of you are actually familiar with it, and what it causes to the wavelength of light emitted by the source moving relative to us, either receding or approaching. So let me explain briefly what the Doppler effect is. I'm sure you've been in a situation where you are on the street and there is an ambulance car or a fire truck rushing to rescue somebody, to provide help. So this is when the ambulance car is approaching you, and here it has passed you by and it's receding from you. And it has its siren on, so what do you hear? High pitch as it is approaching you, and then as it passes you, the pitch drops. The same as if you are watching the car races, right? On a straightaway, when the drivers have pressed the gas pedal to the max, right? The engines, the pistons move at a certain rate, right? They produce the noise, certain frequency, right? But that frequency seems higher as the race car is approaching you than when it passes you on, right? So this is what Doppler effect is. It is the change in frequency or wavelength of sound, or pitch, as we often say, because of the relative motion of, in this case, source of sound and the observer. So as the source of sound is approaching you, the frequency is perceived as higher pitch, and then as source of sound is receding from you, moving away from you, the pitch is perceived as lower. Well, we have the same effect with light. And it's easy to understand what is involved. Let me just explain this. Let's first look at the situation when the source of light is stationary relative to the observer. Okay, so here is the source of light, a star or a light bulb. It doesn't matter. Any source of light would do. And here is the eye of the observer. Now, at the moment when one wavefront of light, remember the wavefront is the plane that rides on the crest of the wave. So the wavefront number 1 hits the eye of the observer. That at that same moment, the wavefront number 2 leaves the source. Then, of course, the distance between two successive wavefronts is the wavelength. So that would be the wavelength of light that you detect emitted by the source. So this is when the source of light is stationary. Now, if the source of light is approaching you, then okay, let's take the moment when the wavefront number 1 hits your eye here, right? Same as before. But now, because the light source is moving towards you, when it emits the wavefront number 2, it is closer to you. And now you detect this distance between two successive wavefronts as a wavelength of light. So now you would perceive the wavelength to be shorter. And we say that this wavelength has been blue shifted. That is, it's reduced in size, and that effect is often referred to as blue shift. Now you can guess immediately that when the source is moving away, okay, so here again is the eye of the observer at the moment when the wavefront number 1 strikes the eye. But now the light source is here, it was approaching, now it's receding, right? And here is the location of the source when the wavefront number 2 leaves it, and now you perceive a longer wavelength than when the source was stationary. So now you have that perceived wavelength is longer than the one that you would detect from a stationary source. And in this case, we say that the light is redshifted because the perceived wavelength is longer than the one that you would detect if the source was not moving relative to you. Okay, so depending on whether the source is stationary with respect to you or whether it's moving towards you or away from you, the wavelength of light will have different values. If the source is approaching you, the wavelength that you detect would be shorter than the one that you would get if the source of light was not moving. If the source of light was moving away from you, if it was receding, then you would detect the wavelength that is longer compared to the one that you would measure when the light source is not moving. And it turns out that the amount of shift of wavelength is determined by the speed of the source, the relative speed of the source. So what the astronomers use is that the change in wavelength over the wavelength that you would measure if the source was stationary is precisely given by the relative speed of the source relative to you over the speed of light in vacuum. Okay? So you measure the amount of shift, either redshift or blue shift, and then you, from the known wavelength that you know, that you measure in the lab when the source is not moving relative to you, you can use this relation to determine the speed of the source. Okay, so delta lambda, the difference between perceived and the actual wavelength is negative in the case of blue shift. When the perceived wavelength is shorter than the one that would be detected from stationary source, and is positive in the case of redshift. So how do we use this Doppler effect to detect the spectroscopic binaries? Well, this is illustrated in the following overhead. So I have two stars that are orbiting around their common center of mass, okay? And at this particular time, star 2 is moving away from me. It's receding. And therefore, its spectrum is going to be redshifted. I would see longer wavelengths compared to what I would see if this star was not moving. So a particular spectral line is redshifted. Delta lambda is positive, right? 0 corresponds to no shift at all. At the same time, star 1 is moving towards me. It's approaching. And therefore, its light is going to be blue shifted. Delta lambda is going to be negative. So the spectral line coming from this star is going to be shifted towards the shorter wavelengths. Now, at the quarter period, when both stars have moved 1/4 of their total orbit, at this particular instant, neither one of the two stars is either approaching me or receding away from me. They're moving in the direction that is perpendicular to my line of sight. So neither star 2 nor star 1 are approaching me or receding. Therefore, their spectral lines are not shifted at all. So the two spectral lines are not shifted and they fall right here. After half a period, I have the reverse situation. Now the star 1 is moving away from me, and its spectral line, the thick one, is going to be redshifted. Delta lambda is positive. The star number 2 is now approaching me, right? And its light is going to be blue shifted. Delta lambda is going to be negative. After 3/4 period, I have the same situation or analogous situation to the one after a quarter of the period, where neither one of these two stars is either approaching me or receding away from me. Therefore, there is no shift in their spectral lines. All right? And then after one period, once each star has completed a full revolution around the center of mass, I have returned back to the initial situation when the star 2 is moving away from me, star 1 is approaching me, and I see the same amounts of shift as I saw at the beginning. So what you do, you look at the star, right? And then you analyze its spectrum. And you see that the spectral lines are doing this. And you say, aha, I actually have two stars that are in a dance with each other, right? They are dancing, they are orbiting common center of mass, and because they are in my line of sight either moving away or toward me or at a given instant neither, right? I will have alternatively redshift and blueshift and redshift and blueshift. So I can measure the interval of time it takes for the spectrum to return to its initial configuration, right? So then I can actually measure the orbital periods of the two stars. From the amount of shift, using that relation that I've written on the previous piece of paper, I can determine their orbital speeds, right? If I know their orbital speeds and I know the period, I can find out the circumference, because I know that they will complete one full revolution in one period, and I know the speed of motion. And I know the distance, the circumference that they travel in one period. From that, I can find the circumference of this circle, and from it, its radius. So again, I can find the orbital data of the two stars, okay? And again, I can use the third Kepler's law as formulated by Newton to find the total mass of the two stars. So although I cannot resolve the two stars as separate in telescopic view, by doing the spectral analysis, by seeing that their spectra oscillate due to Doppler shift because of the way they move, I can find out the masses of the stars.